By the end of this lesson, you should be able to explain what inertia is, relate mass to inertia, give examples of situations involving inertia, suggest ways to reduce the negative effects of inertia. Observe the passengers in the moving bus. What happened to the passengers in the bus? Let us explore this further by looking at the video again. What happened to the passengers? The passengers were thrown forward. Why? When the bus was moving, the passengers were also moving at the same speed as the bus. When the bus stopped, the passengers continued moving. Hence, they were thrown forward. Let us look at another situation. What happened to the people in the car? Their heads were thrown back when the car started moving. What is similar about the passengers in the car and the passengers in the bus from the previous situation? The passengers in the bus continued moving forward although the bus had stopped moving. The people in the car tried to remain in their state of rest when the car started moving. In both situations, the passengers were resisting a change in their state of motion. Galileo called this tendency to resist change in motion inertia. Inertia is a tendency to resist change in motion. It is not a physical quantity. Galileo's concept of inertia was later refined and restated by Newton, another distinguished scientist and mathematician. He called it the law of inertia, and it became his first law of motion. It was first published in Principia in 1687 and is stated as follows. Every object continues in its state of rest or of uniform motion in a straight line, unless it is acted on by an external force. Look at both videos. Which cupboard is harder to push? Which cupboard has the larger mass? Which cupboard has the larger inertia? The bigger cupboard has a larger inertia because of its bigger mass. So, we can say that mass is a measure of inertia of an object. The effect of inertia can be useful in our everyday lives. Let's look at a few examples. What is the use of slamming the hammer? The slamming tightens the hammerhead. How does the downward motion and sudden stopping of the hammer tighten the hammerhead? The hammerhead resists change in motion and continues to move downward when the hammer is suddenly stopped. Here are more examples of useful effects of inertia in our lives. It is easier to get tomato sauce out of its bottle by shaking the bottle in a quick up and down motion. Why? When the bottle is moved quickly towards the frying pan, tomato sauce continues to move in the same direction even when the bottle is quickly moved in the opposite direction. Hence, it gets out of the bottle more easily than waiting for it to drip down slowly. Animals such as cats and dogs dry themselves by shaking their bodies. How is this possible? By shaking its body, the dog moves its body in one direction and then in another direction quickly. Water droplets continue to move in the same direction even when the dog quickly moves its body in a different direction. Hence, the water droplets are sprinkled away from the dog's body. Can you give more examples of the useful effect of inertia in our lives? Inertia can be useful, as in the example of the tomato sauce and dog, and can also be hazardous, as in the example of the bus and car. How can the negative effects of inertia be reduced when a car stops? Injuries can be reduced by the use of seatbelts and airbags. They prevent passengers from being thrown forward. What if we are involved in a rear-end collision or are in a situation involving sudden acceleration? Headrests in cars help guard against neck injuries in a rear-end collision or sudden acceleration.
Here is a steel ball hanging at the end of a string. Predict what will happen when the lower string is pulled steadily with a slowly increasing force. Now, predict what will happen when the lower string is pulled with a jerk. You have seen that the upper string breaks when a steadily increasing force is applied. In contrast, when the string is jerked, the lower string breaks. Why? Only the upper string bears the weight of the steel ball. When the lower string is pulled with a steadily increasing force, the tension supplied by the pull is transmitted to the upper string. The upper string breaks when it reaches the breaking point. In contrast, when the lower string is jerked, the inertia of the ball slows down the transmission of tension to the upper string. Thus, the lower string reaches its breaking point first. Drag and drop to complete the diagram.